From a long time, we have been using chemical sensors for a variety of uses like monitoring chemical processes, detecting poisonous gases in a chemical plant, or analyzing water quality and liquid purity. But most of the methods that we use require the chemical itself to be consumed. So, what if we have to test for a very minute amount of chemical? Let's say if we want to detect very small amount of chemical in gas, or let's say air, or even in a solution. We need this in various fields such as industrial processes, medical diagnosis, and environmental sciences. But how do we achieve this? Thanks to the technological advancements, we now have ways to test chemicals without altering them. Among others, optical chemical sensors are one of the most promising devices because the light probe essentially senses the chemicals in a non-destructive manner. Surprise, huh? Let's have a look at what optical sensors are and how do they work. These sensors comprise mainly of micro-optic components such as optical fibers, waveguides, and microlenses. They use the principle of surface plasmon resonance on a metal film excited by light for analyzing the chemicals. Now let's know more about surface plasmon resonance. On the plasma surface, for example metal, collective resonating oscillation of free electrons may exist, thus producing a wave having charge density propagating along the plasma surface. This wave, called the surface plasmon, is a transverse wave with the oscillating electric field vector normal to the surface. Surface plasmon resonance, or in short SPR, can be excited by an electromagnetic wave traveling through the medium facing the metal. The light to excite SPR should be polarized parallel to the incident plane, that is p-polarized, because surface plasmon has only the electric field component normal to the surface. When the wave vector and the frequency of the incident light coincide with those of the surface plasmon, this light resonantly excites the latter. Krishnan proposed a way to excite SPR by an evanescent wave from a high refractive index prism at the total internal reflection condition. The dispersion relation of the surface plasmon depends on both the dielectric constant of the metal and that of the sample medium phased on the metal. By monitoring the resonance condition of the surface plasmon, the dielectric constant of the sample is obtained. If the sample is contaminated by some chemical species, dielectric constant measurement gives the concentration of the chemical species in the sample as well.
The wave vector Ksp of the surface plasmon on the boundary between a metal and a sample at frequency omega is given by Ksp, where epsilon s and epsilon mr are the real parts of the dielectric constants of the sample and the metal, and c is the speed of light in vacuum. When a light beam is incident through the prism on the surface of the thin metal film at total reflection angle theta, the evanescent wave interacts with the sample and at the proper theta sp angle, it couples with the surface plasmon. The wave vector of the evanescent wave is the same as the lateral component of the incident light wave vector in the prism, that is KEV is equal to kg sin theta, where epsilon g is the dielectric constant of the prism. At the proper theta sp incident angle, the wave vector of the evanescent wave coincides with that of the surface plasmon. Hence, a fraction of the incident light energy transfers to SPR, the energy of the reflected light diminishing, which can be observed as a sharp dip in the reflectance of light from the prism. So now, let's have a look at the schematic of the system. Here silver film is used as a sensing plasma because the damping factor of silver is smaller than that of the other metals available, providing a sharp dip in reflectance. The metal film should be of low thickness and prism should be of high refractive index. So, we can plot reflectance curves of various samples and analyze the substances for purity by measuring the dielectric constants. For example, here are the reflectance curves of water and 5% ethanol in water solution. The accuracy of this setup comes out to be very high, and this is how SPR sensors work. Surface plasmon sensors have found variety of uses in industry and medicine. This is just the beginning of the era of optical sensors. We are moving towards more compact sensors with high resolution. The day is not far when we will be using this technique for biosensors too.